Let us now see the case of quadratic poles or zeros. So that means you have a second order term. Okay. So let us take, for an example, let us take a quadratic pole. So that means g of s is equal to 1 by s square plus 2 zeta omega ns plus omega n square. This is how you represent a second order function, right? Now what are the roots of this equation? We have already discussed in the time domain analysis, right? What are the roots? Minus zeta omega n plus or minus omega n root over zeta square minus 1. Okay. So now what is going to happen? If zeta is greater than 1, then you are going to get real and unequal roots. And if you get real and unequal roots, let us say they are S1 and S2, then you can represent this as the equation 2 zeta omega ns plus omega n square. You can write as S minus S1 into S minus S2. So now what is this becoming? This is becoming a product of two poles, right? So simple poles. So that means just like the simple poles we have discussed, we can draw the magnitude plot of each of this pole and then we can add them up. Okay, so that is how you will get the Bode plot of this function if you have real and unequal roots. But if that is not the case, zeta is not greater than 1, but if it is less than 1 or equal to 1, then what is going to happen? You cannot represent as S minus S1 into S minus S2. That means you cannot get in terms of two simple poles. Cannot write in terms of simple poles. Okay. Here also you can write this is in the form of two simple poles. Okay. So now you can very easily construct the Bode plot. But in this case, zeta less than or equal to 1 cannot write in terms of simple poles. So you cannot use the same procedure. So how will you do in this case? For this case, we will write the magnitude. What is the magnitude function you are getting? What is the phase function you are getting? And then accordingly we will draw the magnitude and the phase plot. First we will draw the magnitude plot. So if you put s is equal to j omega, then g of j omega you are going to get 1 by s square. In terms of s square you will write j omega whole square plus 2 zeta omega n into j omega plus omega n square. Okay, so this you can rewrite as 1 by omega n square divided by 1 minus omega by omega n square. The real parts you will write together plus j 2 zeta omega by omega n. So this is a constant term now, right? So for now we will ignore it. Okay, the constant term can be separately plotted and then can be added along with the magnitude plot of this. So right now we will discuss only the magnitude plot of the pole, only this quadratic pole. Okay, so what will be g of j omega? This is excluding the constant term or excluding 1 by n omega n square term. This is going to be 1 by root over 1 minus omega by omega n whole square. This whole thing will be square plus 4 zeta square omega by omega n whole square. Then what about the magnitude in dB? This is going to be 20 log g of j omega. So this you are going to get minus 20 log, this whole thing will come. Okay, 1 minus omega square by omega n square whole square plus 4 zeta square omega square by omega n square. Here you will have to do some approximations just like in the case of simple pole or simple zero. What is that approximation? For very small frequencies, for very low frequency, that is omega is much less than omega n. Then what will happen? Omega by omega n is much less than 1. So now what will happen? Here you have 1 minus omega square by omega n square. This term will become negligible with respect to 1. Here also you have omega square by omega n square, and zeta is anyways less than 1. So this term will also be negligible as compared to 1. Therefore, magnitude in dB you can approximately write as minus 20 log 1. So what we have done here, this term and this term we have taken as negligible, which is true because the frequency is very low. So what are you going to get here? This is 0 dB. So that means for low frequencies you can approximate the magnitude plot as a 0 dB plot. Then what about the case of high frequency? For very high frequency, that is omega is much greater than omega n. So in this case what will happen? Omega by omega n will be much greater than 1. Okay. So then the magnitude, therefore magnitude in dB you can approximate as minus 20 log root over omega square by omega n whole square plus 4 zeta square omega square by omega n square. But this term also you can take as negligible. Why? Because here you have omega by omega n whole to the power 4. Here there is only square term. In addition, what we have here, zeta is less than 1 and zeta square is present. So this whole term will become negligible. So what will you be left with? You are going to be left with minus, or you can write approximately minus 20 log omega by omega n whole square. This is going to be what? The 2 power you can take it out. So you are going to get minus 40 log omega by omega n. So you can see that here the slope is minus 40. Okay. For a simple pole it was minus 20 dB per decade, but for a quadratic pole you have got minus 40 dB per decade. So you are going to get a straight line with slope minus 40 dB per decade. This is the second asymptote. Now you can draw the magnitude plot. This is magnitude in dB and here we have the frequency omega. Now if you draw the two asymptotes, first we will draw the asymptotes. One is what? At 0 dB. Let us take this to be 0 dB. And the next line, it is a line with slope minus 40 dB per decade. Okay. So this is minus 40 dB per decade. Now where will they both meet? That means what is the frequency at this point? This you will get by equating both the straight line equations. So that means minus 40 log omega by omega n you should equate to 0. Then what will you get? Omega by omega n should be equal to 1, meaning that omega is equal to omega n. So omega is equal to, at omega is equal to omega n, you have the point where the two asymptotes meet. Okay. The actual plot will be somewhat different, but we are not concerned about that right now. We are only concerned with the approximate plot. The actual plot will depend on the values of zeta. For different values of zeta, you are going to get slightly different forms. Okay. This is not as direct as the simple pole or the simple 0. Okay. So this is the approximate plot. And these are called as the asymptotes. Now what about the phase plot? So the angle g of j omega we can write as, what was the function? G of j omega is equal to 1 by 1 minus omega by omega n whole square plus j 2 zeta omega by omega n. So now you can write phase minus tan inverse 2 zeta omega by omega n divided by 1 minus omega square by omega n square. Here also you have to do some approximations. For low frequencies, what we can write? Omega by omega n we can ignore as compared to 1. Then what will be the phase? The phase G will be equal to minus tan inverse 2 zeta omega by omega n. And here if you substitute omega is equal to 0, that means the initial angle, then angle G is going to be equal to 0 degrees. Now what happens for high frequencies? For high frequencies, omega by omega n you can take to be much greater than 1. So this will give you mod G is equal to, now you will have to ignore this 1. So then what will you get? Mod G, angle G is equal to minus tan inverse 2 zeta by minus omega by omega n. Now this is a negative real number, right? So negative real number means that tan inverse of a negative real number is what? 180 degrees. So you're going to get, but negative is also there, so you're going to get minus 180 degrees. Okay. So as the frequency increases, the angle will change from 0 degrees to minus 180 degrees. So is it going in this direction or in this direction? That we will know if you take out an angle in between. Okay. So for that we will take, what will be the angle for omega is equal to omega n. That is omega by omega n is equal to 1. So you can see the denominator will become 0. So angle G will be minus tan inverse of infinity, which is giving you minus 90 degrees. So the angle will change from, or the phase will change from 0 degrees to minus 90 degrees to minus 180 degrees. So that means in which direction? It is going to go from 0 to minus 90, minus 90 to minus 180. Okay. So the phase plot finally you can draw. This is the phase with respect to omega. So if you have 0 degrees here and minus 180 degrees here, it is going to go like this. Okay. At omega is equal to omega n, you're going to get minus 90 degrees. So till now we have seen the case of a quadratic pole. What about the quadratic 0? That means G of S is S square plus 2 zeta omega n S plus omega n square. So here also the same procedure will be there, but the plots will just be inverted about the 0 axis. That's all. Okay. So we will directly draw these plots. If this is 0 dB, then the plot is going to be like this first, and then it will be a slope of, it will be a line of slope plus 40 dB per decade here. Okay, it is increasing, slope is increasing. For a quadratic pole, it was decreasing at minus 40 dB per decade, right? So what is this frequency here? Omega n. This is the frequency axis and this is the magnitude axis. Similarly, what will happen to the phase? It will start at 0 degrees, let us say this is 0 degrees, and then it will keep increasing to 180 degrees. And at omega is equal to omega n, the phase is going to be 90 degrees. Now the final function that we have is the pure time delay function. So how will you represent this? G of S is represented as e to the power minus STD. Okay. So we will see what is the magnitude and the phase plot. First you will write in terms of omega. So substituting S is equal to J omega, you are going to get e to the power minus J omega TD. Then what will happen to the magnitude? Mod G of J omega is equal to simply 1. Then in dB what will be the magnitude? 20 log G of J omega is equal to 0 dB. So that means the magnitude plot is a constant, which is 0 dB. Then what about the phase? The phase is going to be minus omega TD. So as frequency increases, the magnitude of the phase will increase, but in the negative direction. So now you can draw the Bode plots. This is magnitude as a function of frequency. So you're going to have a constant plot at 0 dB. And what about the phase plot? The phase plot as a function of frequency, it is going to start from 0 degrees and then it is going to fall with increase in frequency. Now we will take an example and try to get the Bode plot of this function. So what is the function given here? 5 into s plus 0.1 divided by s into s plus 0.05. Till now we have discussed only a simple 0 or a simple pole, right? But now we have a combination of functions. So how to use all of our concepts that we've already learned to draw the Bode plot of this function. Okay. So the very first step, whenever it is given in the pole 0 form, this is called as the pole 0 form. Okay. That is when you write as s plus z1 into s plus z2 and so on. And in the denominator you are going to write as s plus p1, s plus p2 and so on. This is called as the pole 0 form. So the very first step involves writing in the time constant form. Okay. So step 1, express the function in time constant form. So how will you write in time constant form? What is the time constant form? When you write as 1 plus s into t1, 1 plus s into t2 and so on. And in the denominator you can use a different subscript, 1 plus s into ta, 1 plus s into tb and so on. Okay. So now this function that we have, if you write in the time constant form, what are you going to get? 5 into 0.1 you take out common, so that you're going to get s by 0.1 plus 1 divided by, similarly you will take out 0.05 here. So 0.05 into s by 0.05 plus 1. So now the constant, new constant will be 5 into 0.1 divided by 0.05. So what will that be? 10. Okay. And here 1 plus 10 times into s divided by s into 1 plus 20s. So this is the transfer function in time constant form. In the same step only you can write in terms of the frequency as well, right? Putting s is equal to j omega, the transfer function you're going to get as g of j omega is equal to 10 into 1 plus 10 j omega divided by j omega into 1 plus 20 j omega. Okay. Now what will be the second step? You have to identify the corner frequencies. So how will you identify the corner frequency? For each of the simple pole or the simple 0, you're going to have a corner frequency. What will that be? Here 1 plus 10 j omega is present. So this 10 omega, the imaginary part you will equate to 1. So that omega you're going to get as 1 by t. Okay. So that means if it was in the time constant form, so this is the time constant form, right? So you write it down here, otherwise you will forget. What will be the corner frequency here? Corner frequencies will be 1 by t1, 1 by t2 and so on. This is for zeros. And what about the corner frequencies of the simple poles? They are going to be 1 by ta, 1 by tb and so on. This is with respect to the poles. Similarly, for whatever function you have here, you have to identify the corner frequencies. Okay. So the corner frequencies that are corresponding to zeros is given by 1 by 10. And what about the corner frequency corresponding to poles? You have 1 by 20, right? You have only one pole and one zero. So you have only two corner frequencies. Next, step 3 is finding out the initial value and the slope of the Bode plot. So this will depend on the poles or zeros at origin. So why is this the case? We know that for a simple 0 or a simple pole, before the corner frequencies, the magnitude is going to be 0. Okay. So only the magnitude is only contributed by the pole or 0 which is present at the origin until the corner frequency, until the lowest corner frequency. See here what is the lowest corner frequency? The corner frequency corresponding to the pole 1 by 20, right? This will be 0.05, this will be 0.1. So the lowest corner frequency is 0.05. Now for frequencies lesser than 0.05, the magnitude is contributed only by the pole or 0 at origin and also the constant term, right? So you can write for frequencies less than the lowest corner frequency. In this case, it is 0.05. Okay. For frequencies less than the lowest corner frequency, the magnitude is given by 20 log k will be the magnitude because of the constant term minus 20 log omega. This is for one pole at origin. Okay. But in general, if you want to write for n number of poles at origin, then what will it be? For n number of poles at origin, the magnitude is going to be 20 log k minus 20 log omega to the power n. And n you can take it out of the argument. Then what you are going to get? 20 log k minus 20n log omega. This is for n number of poles at origin. What about if there are n number of zeros at origin? For n number of zeros at origin, the magnitude you are going to get 20 log k plus 20n log omega. Okay. Here we have a pole and that too only one pole. So n is equal to 1. So here 20 log k minus 20 log omega. So the initial value will depend on what is the frequency that you are taking. If you are taking the plot to be starting from omega is equal to 1, then initial value will be simply 20 log k. If you take omega as 0.1, then it is going to be 20 log k minus of 20 into 0.1. Okay, so we will write it down, don't worry. This is about the magnitude. Then what about slope? Once again, it will depend on the number of poles or zeros, right? So what will it be? For n number of poles at origin, you are going to have minus 20n dB per decade. This is the slope. Okay. Then for n number of zeros at origin, if it is n number of zeros at origin, then you are going to have the slope to be plus 20 times n dB per decade. Okay. So this is how you get the slope. So for the given function, the initial magnitude, let's take the initial frequency to be 0.1. You always have to pay attention to what is the initial frequency being taken. Okay. So then what will be the magnitude? Then magnitude is going to be equal to 20 log k. But here anyways k is given as 10. So you can directly write 20 log 10 minus 20 log omega we are taking as 0.1. So it will be 0.1. Log 10 is anyways 1. So you are going to get 20 here minus 20 log 0.1 is minus 1. So you are going to get 40 dB. This is the initial magnitude at when you are taking omega is equal to 0.1. Always be careful what is the initial frequency. Okay. Then what about slope? This is equal to minus 20 dB per decade because there is only one pole at the origin. Finally, we have the last step. In step 4, we have to change the slope. Like initially it is going at minus 20 dB per decade. Each time there is a corner frequency, we will change the slope depending on whether the corner frequency is corresponding to the pole or the zero. Okay. So at each corner frequency, change in slope will be plus 20 n dB per decade for nth order 0. If it is a simple 0, then n is simply equal to 1. Okay, and for an nth order pole, that means if the corner frequency is corresponding to an nth order pole, then the change in slope at the corresponding corner frequency is minus 20 n dB per decade. Now using all this, we will try to complete the Bode plot, the magnitude of the Bode plot. Okay, phase we will do once again. So this is the magnitude and this is the frequency. Let us take the initial frequency to be 0.1. For 0.1 we have found out the magnitude. What was the magnitude? We found it out to be plus 40 dB, right? This is 40 dB and the slope was minus 20 dB per decade. So you can write here, let's say this is 40 dB. From here it is starting to go down at a slope of minus 20 dB per decade. So now it will reach the 0. Let us take this to be 0 dB. So it will reach 0 dB at one point. Now whether the lowest corner frequency will be before this point or after this point, we have to first find that out. Okay. So what is the magnitude? This is given by 20 log k minus log 20 log omega. Now you want this to be 0, right? When will it reach 0 dB? At what frequency? So this will be equal to 0 when omega is equal to k. So remember, this is only for the single pole at origin. Okay. So k here is 10. So omega is equal to 10. Okay. So this is going to be omega is equal to 10. Anyways, the corner frequencies are much less than that. What are the corner frequencies? The corner frequency corresponding to the 0 is given by 0.1 and the corner frequency corresponding to the pole is 0.05. Okay. You can see that this corner frequency is much less than what we took initial, right? So we will not get a proper idea because the corner frequency is less than the initial frequency. So it is better we take omega is equal to 0.01, much less than 0.1. So here omega is equal to 0.01. Then what will happen to the magnitude? Magnitude at omega is equal to 0.01 will be 20 log 10 minus 20 log 0.01. Log 0.01 is minus 2. So you're going to get 60 dB. Okay. So you can correct here. This is going to be 60 dB. Okay. So now let us say 0.05 will be somewhere here and 0.1 will be somewhere here. Okay. So then at 0.05 the change in slope is going to be minus 20 dB per decade because we have a pole here. Okay. So initially also it was going at minus 20 dB per decade only. So when further the change will be minus 40 dB per decade. So it will go down further. Okay. So this slope is minus 40 dB per decade. So this will continue till what time? Till omega is equal to 0.1. Okay. Once again, what is going to happen here? You have a change in slope of plus 20 dB per decade because this is corresponding to the 0. Okay. So now the plot will once again, the slope will increase. Okay. So this is minus 20 dB per decade. Okay. So this is the Bode plot, the magnitude Bode plot. Next we will see the phase plot. So phase plot, you can either take the actual function, that means g of j omega was what? 10 times 1 plus j 10 omega divided by j omega into 1 plus j 20 omega. Okay. So from here you are going to get angle G is equal to tan inverse 10 omega minus 90 degrees minus tan inverse 20 omega. So now you can substitute the values of omega and then you can get a rough plot of the phase plot. This is the direct method. Another method that you can do is, just like you can add the magnitude plots, you can add the phase plots of the individual functions. What are the different functions that you have here? First one is you have a pole at origin, and then you have a constant term, a simple 0 and simple pole. Okay. Now what will be the plot of pole at origin, the phase plot? It is going to be constant at minus 90 degrees. This is minus 90 degrees. This, let us say, it is 0 degrees. Okay. Then what about, this is for pole at origin. Then what about constant? This is going to have a constant value once again, but 0 degrees. What about simple 0? This is going to be, it will start from 0 degrees and then eventually it will reach to 90 degrees. Finally, what about the simple pole? This is going to start at 0 degrees. So this is 0 degrees and it will reach minus 90 degrees. But when compared to the simple 0, it will go at a faster rate. Why that is the case? Because the function here is 1 plus j 20 omega. The phase here is tan inverse 20 omega. This is tan inverse 10 omega. So as omega increases, this phase will increase at a faster rate because it is 20 omega. Okay. So here what you can do is, it will reach minus 90 degrees faster than the simple 0. Okay. So you can draw here. This is where it is reaching minus 90. Whereas simple 0, it is reaching the plus 90, the final value after the simple pole has reached minus 90 degrees. Okay. Now you can add all of these together. This constant term, anyways, the phase is 0 only, so it won't account to anything. Now these three only you have to add. So the final function, what you're going to get, final phase plot, this you obtain by adding the individual plots. So it is going to be something like this. Here it will start at minus 90 degrees and it will once again end at minus 90 degrees. So this minimum value you can find by differentiating the phase function. It is not very important. We just need to know that the form of the phase plot is going to be like this.